Welcome to SMR X Hackathon Design Challenge lecture series. My name is Sharman Perera. Today we have Dr. Jennifer McKellar talking about renewable energy.
Hello, everybody. I think I will turn off my camera as I switch to the slides. Let's see. So, oops, hopefully everybody is seeing slides. If you're not, please let me know.
Yes, we are.
Okay, excellent. Oops. Okay. So renewable energy is a broad topic. So it's going to be sort of a high level overview, and then with a little bit of extra detail on solar PV and a little bit on wind. So I thought it might be helpful just to sort of start off by outlining where we are currently in terms of our use of renewables, and why we're considering using them, why we want them, as well as some of the downsides to them, why we're not using them more. And then I thought I'd step through some of the different applications of renewables in different areas. So to start off, we've got an image here showing the global primary energy supply. So worldwide, where is our energy coming from? And from here, you can see we're really dominated by fossil fuels, right? Oil, coal, and natural gas still make up the majority of our energy. Nuclear is a respectable chunk. It's not widely used around the world. And then our renewables, including the use of waste, represent about 14% of our global energy use. In Canada, we're sort of similar. It depends on whether we're looking at total primary energy or electricity. So in terms of total primary energy, again, we're dominated by our fossil fuels, oil and natural gas. Oil would be used a lot in for transportation, so our source of gasoline and diesel. Natural gas, of course, used for electricity generation as well as for home heating. And then we've got a smaller fraction of coal that's still used in some provinces. We've got nuclear, hydro, and our other. And so our renewables fall into this other category. Though this other category, our renewables represent about 5% of our total primary energy supply. So that's biofuels and waste, wind, solar, etc. If we include hydro in that number, we're up to about 16% of our total primary energy supply. So that's not too bad. I should say that, I mean, when it comes to choosing energy sources, countries and provinces tend to use what they have, right? The less you have to import, generally preferred. So in Canada, we're lucky in that we've got a pretty wide range of energy resources available that we can choose from. So we've got big reserves of oil and natural gas. We've got uranium reserves. We're also lucky in that we have a lot of hydro available to us. It's not evenly distributed across the country, of course, right? So our oil resources tend to be out west and off the east coast. Hydro is widely used in British Columbia, Manitoba, and Quebec. So it depends on what we've got. If we look at electricity generation in particular, so neglecting heating, industrial uses, and transportation, our renewable fraction is much better. If we include hydro, we're up around 65%. It's worth noting that not everybody likes to include hydro in a renewable energy description. Some of the big, large-scale hydro can have large negative environmental impacts. So sometimes it's reported separately from other renewable energy sources like solar and wind. If we exclude hydro, then our renewable contribution from wind, solar, tide water, and biofuels, if we put just those together, we're at about 6%. If we zoom in a little bit more, specifically looking at Ontario, we've got two graphs here. The one on the left is showing installed capacity. So these are the generating sources that are actually sitting in the province and how much energy they could produce in best case scenarios. And then on the right is the electricity generation. So how much electricity is actually being generated from those sources. You'll notice that on the left, we've got transmission and distribution, and on the right, we've got transmission only. So I'll come back to that in just a sec. So for our installed capacity in Ontario, we've got a pretty good mix, right? So we've got a big fraction of nuclear, some gas, oil, good fraction of hydro, wind, solar is actually showing up on the graph now, so we can see its contribution, and then a little bit from biofuels and other resources. In terms of where our electricity actually comes from, though, so how much, when we turn a switch and the lights come on, where is that electricity actually coming from? In Ontario, we tend to be about 60% nuclear, a big chunk from hydro, wind, our solar contribution is small again. So again, this figure on the right is transmission only. So a lot of the solar that we have in Ontario is not connected to the provincial transmission grid. It's connected to the distribution grid. So our big chunk over here in terms of capacity is not really comparable to our generation on the right-hand side. So the left-hand side figure is showing everything that's installed, sitting on the ground, able to operate. And the right-hand figure is showing what's actually operating and being connected to the provincial grid. So we probably do have more solar. It's just it's being used locally, not being used provincially. Okay. So what are the pros and cons of these different technologies? There's a lot of them. So I just sort of picked and chose a few of them. In terms of conventional energy supply, everyone is sort of familiar with the problems with it, right? But why do we keep using it? Reliability is a big factor, right? So these technologies are mature. So by mature, it means they've been around for a long time. We know how they work. We know how to fix them. The supply chains are all in place. It's reliable, right? No one wants to be in a situation where something goes wrong and the power goes out, right? You want, especially if you're looking at planning from a provincial or a national level, you want technologies that you know are going to work, how they work, and they're going to work well. Even things like cars, right? So there's electric cars on the market. Not many people buy them. Partly that's because it's unfamiliar, right? Well, I could buy an electric car, but what if it breaks down? How am I going to get it fixed? I don't really know how it works. I've never driven one before. That becomes a factor in people's decision making, right? And that's something that's hard to overcome. And sometimes it's just going to take time, right? As more and more of these technologies are used over time, they'll become more familiar, and they should be easier to replace the conventional technologies. Conventional energy also tends to be less expensive than renewables. That's not necessarily the case anymore, so we'll get to that in a minute. But generally, the least cost resources are used first, right? So no one's going to pay $10 a kilowatt hour if they could be paying 10 cents a kilowatt hour. It just doesn't make sense. So our conventional technologies, partly because they've been around for a long time, they tend to be inexpensive. They also tend to be integrated with economies, which can't be sort of underestimated, right? Large industries have a lot of people working in them. Those people have jobs. They need to be able to buy food and housing. There are whole supply chains. So you might have one coal-fired power plant, but then there's equipment manufacturers for that power plant, and there's coal miners, and there's the people who make the trucks for the coal mining. So it's not necessarily just shutting down a plant, it's a big system that you need to consider when you're talking about conventional energy supplies. So it's not a quick fix. It's not an easy change to move away from conventional energy supplies. But then again, we do have the downsides, right? So our fossil fuels, when we combust a fossil fuel, we release carbon dioxide um, along with other greenhouse gas emissions. Natural gas is largely methane. So when we combust natural gas, we release carbon dioxide, but throughout the life cycle of natural gas, we're also kind of leaking, right? Whenever you process it, there's going to be some leakage, and that methane is a strong contributor to climate change. Smog is another one. We don't hear, so I'm a little bit Toronto-centric at the moment, but we don't hear so much about smog anymore since Ontario closed down our coal-fired power plants, right? Land use change is another one. So a conventional electricity generation plant, for example, maybe doesn't have a huge footprint in terms of land area, right? It doesn't take up much space on a map, but the mining process, for example, could. Or if we're looking at transportation, like a gas station is a very small footprint, but we've got pipelines, we've got oil wells spread across a landscape. So there are land use impacts as well. And then, of course, there are impacts on human health. So, for example, emissions of particulate matter are quite hazardous to people's health. So they would be emitted from, for example, the combustion of coal. They're part of smog. And so there are deaths and hospitalizations in an urban area that can be attributed to air pollution, which is a consequence of using our conventional energy supplies. So when I said back here that our conventional energy supplies tend to be low cost, that's because we're not putting a dollar figure on these negative environmental and health impacts. So these are called externalities. So they're kind of external to the cost calculation. Whether they should be or not is arguable, right? So for example, when we put a price on carbon, we put $20 per ton of CO2 emitted charge. That's taking that externality and bringing it into the calculation. So we put a price on the carbon, and now all of a sudden this environmental impact of climate change has an economic cost associated with it, and that's going to have an impact on this low cost parameter. Okay, so that's sort of the picture of conventional energy supplies and why we're still using them, and why it's hard to shift away, but then we have reasons why it's a good idea to do so. So if we're going to shift away from conventional energy, and we're really going to have to replace it with something else, right? We can reduce our energy use, we can increase energy efficiency, but we're not going to be able to totally get rid of it, right? So we're going to need to replace our conventional energy supplies with something else. Renewables are one of the options available to us. And so I have a slide with different renewable energies, but just to sort of frame the discussion, we've got wind, solar, biofuels, hydro, right? So our technologies, some of them are mature. We think of renewable energy as being sort of cutting edge and brand new and something we haven't really tried before. But in reality, it has been around for a long time. Hydro, for example, we've been using for hundreds of years at least. It does tend to be less familiar though, right? So hydro is one that we are used to, but something like solar, even though solar has actually been around for a long time, it's something that still seems quite new to us, right? So if you were thinking of putting a solar panel on your roof, you might be concerned, well, I don't really know how it works. Nobody else has one. Why would I want to do that? So the familiarity is still not really there. Some of them are also intermittent, right? So like solar and wind, you can only generate electricity when the sun is shining or the wind is blowing. And so our conventional energy technologies tend to be a little bit more controllable, right? So if we want more power, we turn on the coal-fired power plant and we let it run until we don't want power anymore. We can't do that with a solar panel, right? It's going to generate power when the sun is out, and it's when the sun goes down, it turns off. So we need some other components in our energy system to balance that out. It might be energy storage. It might be a different energy technology that's going to work in tandem with the solar. Traditionally, so renewable energy has been, so again, I should specify, so technologies like solar have been more expensive than our conventional energy supplies. Hydro is not generally considered an expensive type of energy. Building a new big hydro plant can be extremely expensive. So they're building new plants, for example, in Newfoundland and in British Columbia. And so that capital cost, the amount of money up front, can be huge. But once it's built and running, then there's relatively low cost, right? And they operate for a long time. Things like solar is still relatively expensive. The cost has come down a lot in recent years. Over the last sort of 15 years, it's gone down considerably. Wind is actually, I've seen some numbers that say wind is less expensive than a new natural gas combined cycle power plant. So the more we pursue these renewable technologies, the better we get at manufacturing them, the more experience we get installing them, the more experience we have operating them, the more the costs should decline. And so we're starting to see that now with some of our renewable energy technologies are competitive with conventional technologies. Renewable energy is not perfect. So as I said, we have the problem of intermittency, and we have problems with cost in some cases. They also, I mean, they're not perfect environmentally either. So the energy density of a lot of renewable energy technologies is quite low. So to get the same amount of energy as a natural gas fired power plant, you would need a considerable land area for solar, right? So that takes up land. So that's a problem. It can also have impacts on wildlife. So it might be habitat destruction. It could be using farmland. That's obviously not ideal. So there are options to put solar on rooftops, for example, right? That's sort of a better approach. But again, you do need a lot of area to get a significant amount of power. There are also impacts on humans. So I've got aesthetics here. So wind turbines are often seen as from a negative perspective. So if you go to a community and say you want to install a wind farm, sort of on the outskirts of town, for example, I would expect that the people living in that town would not be happy because, you know, they like their rural environment, they like the natural environment as they see it. They don't necessarily want to be looking at wind turbines, right? And I mean, there are financial implications as well, right, in terms of property values. Another one I could have put here would be noise concerns, right? A lot of people have concerns about the vibrations from wind turbines. And there's been various studies looking at trying to quantify that. So renewable energy, it's got a lot of things going for it. It doesn't have any greenhouse gas emissions at source, for example, from a wind or a solar facility. But it does have its own, it's not perfect, right? Not everybody is going to be super excited to have renewable energy installed nearby. Okay, so that sort of a high level description of conventional versus renewable energy technologies and why we use some and not others, and the different factors that need to be considered. Just to sort of take one more step back and look at where we are in Canada right now in terms of renewable energy. So this is sort of building on the data we saw previously. So if we look specifically at renewable energy in Canada, looks like, I'm not sure if you guys are seeing this there. So most of our renewable energy is from hydroelectric power. And as I said, we're sort of lucky in Canada that we have that resource available to us. We've got some use of solid biomass, wind, ethanol, and we'll come to that sort of at the end. And then our solar thermal and our tidal are small. They don't really show up on our graph here. In terms of where Canada is relative to other countries, we rank 7th in terms of total production. But again, that's really thanks to our hydro resources that we have available. And relative to other countries, we do get more of our energy from renewables than from conventional sources. Okay. Oops. All right, so I said I was going to talk about electricity, heating, and transportation. I've got sort of the most information on electricity. So just to give sort of an introduction, I've got images here of the different ways that we can use renewable resources to generate electricity. So we've already talked quite a bit about wind. So this is sort of the familiar wind turbine that we're used to seeing. If you drive, for example, down to southwestern Ontario, you drive through a lot of wind farms. This is a solar PV installation. So this looks like a monocrystalline silicon photovoltaic panel. So that's sort of the traditional type of photovoltaic or PV technology. And this is probably a tracking system. So you've got an array of modules. So each little black spot is a cell. Each rectangle is a module. And when we put a bunch of modules together, that gives us an array. So we've got an array on what looks like a pedestal, right? So this is probably a tracking system. So as the sun moves across the sky over the course of a day, this array is going to rotate so that it's always got the best angle to the sun. So you're always generating the most amount of energy that you can. This is the type of solar system that we most often think of when we talk about electricity from solar energy. This is a different type of solar energy system. This is a concentrating solar plant. I've got a different picture coming up later. So this is a power tower type design, it's called. So what you can't see too well is the ground around these towers is covered in little mirrors called heliostats. And the sun comes down, it hits the little mirrors, and it bounces back up to this centerpiece. It heats up a working fluid. It could be water or maybe a molten salt. And then that heat is used to generate steam, to turn a turbine, run a generator, and that's how we get our electricity. So we'll come back to that in a bit. This is a picture of Niagara Falls. It doesn't have the actual generating plant shown, but even just looking at the water, you can get a sense of the power that's available to us, right, in Ontario from Niagara Falls. We've got biomass. So a biomass plant would tend to a biomass electricity generating plant would probably not use logs. They would have their biomass in the form of pellets. But for example, in Ontario, Atikokan up near Thunder Bay was converted into a biomass fired plant. And then this image here is showing representative of geothermal energy. So when we think about geothermal, we tend to think of it as heat, right? If we just wanted to use it to heat our homes, for example. But if you've got a good a good geothermal resource, like in Iceland, for example, where you've got essentially steam underground, it's hot enough that you can actually use that that heat from underground to turn a turbine, run a generator, and get electricity from geothermal that way. Okay, so this is sort of a number of ways that we can produce electricity using renewable energy resources. Obviously, I haven't shown them all. We saw earlier that in Canada, we do have some electricity generation from tidal resources, for example. So that's another technology. Some people are working on developing ways to extract energy from waves. So as waves pass by, a buoy kind of bounces up and down, and you can generate electricity from that as well. So this is just sort of a snapshot. But I thought I would spend just a little bit more time on PV cells, since that tends to be what we think about. So I mentioned earlier that we tend to think of renewable energies as brand new, cutting edge type of technologies. But PV cells have actually been around for a long time. They haven't been economic or especially efficient for very long, but they have existed for quite a while. So in 1839, Becquerel first discovered the photoelectric effect. So the fact that you could, if you shone light on a material, you could have current develop. In 1954, a PV cell was developed at Bell Labs in the US. So this was more like a PV cell, more similar to what we're used to today. They've obviously missed a lot of steps here, right? But so sort of 1954 is sort of the precursor to what we have now. In 2018, globally, there were 505 gigawatts of solar capacity installed. So that's a pretty fast evolution, right? So from the first cell being developed in 1954 to 2018, so 65 years or so, we've got 505 gigawatts installed globally. In Canada, we have a smaller fraction, 3 gigawatts, and that's partly due to the solar resource that we have available to us. And so we'll get to that coming up. So how do photovoltaics actually work? So I've got sort of a simple cross-section of a monocrystalline silicon cell. So as I said, the monocrystalline is the traditional type of PV panel, right? Silicon is a semiconductor material. So at low temperatures, it acts as an insulator. But if we add heat or light, it can become a conductor. So a monocrystalline cell is actually a combination of two layers. So we've got a back contact. Then we've got what's called a P-type layer, an N-type layer, and then these contact fingers, which collect our current. So both of these layers are silicon, but they've been doped with different materials. So the P-type layer is silicon, but we've replaced some of the silicon with boron. So picture a lattice of silicon atoms, sorry, and we've taken out some of those silicon atoms and replaced them with boron. Silicon has 4 valence electrons, whereas boron has 3. So when we replace some of the silicon atoms with boron, we end up missing an electron. So now we've generated some holes in our material. The N-type layer is also silicon, but it's been doped with phosphorus. So we've got our silicon lattice, we've taken out some of the silicon atoms and replaced them with phosphorus. Phosphorus atoms have more electrons than silicon. So in the N-type layer, we've got some extra electrons. Okay, so in the N-type, we've got some extra electrons. In the P-type, we've got some missing electrons. So we say we've got holes. And so we end up with a charge barrier or a potential barrier developing at the interface of these two layers. So what actually happens when we want to generate electricity using our PV cell, this is showing a silicon atom. We've got a valence band of electrons and a conduction band around there. So a photon comes in, so a photon of light, it's got energy associated with it. If it's got the right amount of energy associated with it, it's going to transfer that energy to an electron that's been sitting in the valence band of our silicon atom. The electron's going to take that energy, it's going to jump up to the conduction band. And now that electron is free to, say it was made here, right, in the p-type layer, it's free to travel all the way up to our contact finger. It's going to go through a wire, it's going to run through our light bulb, generate some light for us, and it's going to come back down and complete the circuit. Okay, so the way we actually generate electricity using a PV panel is the photon comes in, it transfers its energy to an electron, the electron jumps from the valence band to the conduction band, and now it's free to go where we need it to. The photon energy, if it doesn't have enough energy, to get the electron to jump, then we just get heat production. If it has too much energy, then the electron will jump, but we'll also get some heat production. Okay. Contrary to what you might think, solar panels actually work worse when things are hot, so that we'd like to minimize that heat production. So different ways there's a sort of a whole a lot of things you can do to improve the design of photovoltaic panels. One of them is to use different materials that have different band gaps, so different amounts of energy that the electrons need to jump, and then you can use more of the photons of light coming in, right? Because the sun emits light across a spectrum, so lots of photons coming in with lots of different energy levels attached to them. Okay, so that's our PV system and how it sort of works. So PV, you often hear it described as photons in, electrons out. So it's very simple, no moving parts, right? The only moving part would be if you had, this type of system, right, where you wanted to rotate the panel and follow the sun as it moved across the sky over the course of a day, right? A concentrating solar plant also does tracking. It has a few more pieces to it. So this figure on the right is showing different types of concentrating solar plants. So this one down here, the central receiver or power tower, that's the one we saw before. And so this is another picture of you can see the tower in the middle here, and you get a better sense of all the heliostats or little mirrors spread out all around the base of the tower, right? You can also get a sense of scale, right? This is like taken from a long way away. You can kind of see a road, I think, down here. And so it's a huge land area that's used. This parabolic trough system is also quite common. So it works by the same principle. The sun comes in, it hits these mirrors, and then it's redirected to the center tube. So in the power tower, the sun hits the mirrors and it's directed to the central receiver. In the parabolic trough, it's directed to the central tube. In both cases, it's heating some kind of working fluid that's going to take that heat away, generate some steam, for example, run a turbine, run a generator, and that's how you get your electricity. Okay, and then we've got a couple other systems here. Same basic idea. The linear system, just instead of it being curved, they're flat, long mirrors. And then this dish system that looks a bit like a satellite dish, right? This figure here is just showing that same system a little bit more schematically, so you can get a better sense of how the energy transfers, right? So the solar energy comes in, reflects off the mirror. So one of the keys with this type of system is making sure that all of those little mirrors are facing the right direction at the right time of day, right? The sun is going to move across the sky over the course of a day, and you need to make sure that your mirrors are following it and always directing the light back to this central point. So that can be complicated, right? You need an algorithm to control the panels. Some of the PV systems, a simple PV system, You could have a computer controlling how it tracks the sun. You could also have someone just go out and move it a few times a day, right? Like physically shift the panel a few times a day. The other thing with the concentrating solar systems is that you need what's called beam radiation. So you need direct sunlight, clear sky type of sunlight. A PV system will generate more power on a clear day in direct beam radiation, but it will also generate some power on an overcast day, or if it's not directly getting a beam of sunlight on it, right? So if you didn't move your panel, and so the sun was sort of off to the side, as long as some light was still hitting it, you'd get some power. With the concentrating solar panels, you really need beam radiation at the right angle. You also have to keep your mirrors clean. So this one is sort of like in a vegetated field. This one is, I believe it's in Arizona, perhaps more of a desert environment, and so there's dust, right? And so you need, if you want your light to reflect off your mirrors properly, you need to keep them clean. So that's washing the mirrors is another piece of the puzzle for getting these CSPs to work. So for solar energy, just because we've sort of said a fair bit about it, the advantage is we have no emissions at the point of generation. So there's no combustion, so no greenhouse gases, no smog emissions. The PVs are relatively simple to operate. The concentrating plants take a little bit more work. And our PV costs have come down dramatically. So in 2000, we were at about $10 a watt. And by 2013, we were less than $1. So that's a big drop in a relatively short amount of time. The disadvantage is that solar doesn't work well everywhere, right? So these concentrating plants that need the beam radiation, they work best in, for example, in the southern US, right? There was one that I found in Canada. I'm not sure it's still operating. PVs have a bigger range, but still, so if we look at this map of Canada, the red is the best solar resource, right? And the blue is the worst. So this is average daily global insolation, or amount of energy from the sun that we're getting. And so you can see for most of Canada, we're not great, right? If red is the best, we've only got a little bit of really good resource available to us. And then, of course, because we're far north, in the winter, our days are really short, right? So in the Arctic, in the territories, they do have some solar panels and some solar systems, but in the winter, they're not going to generate at all in some cases, right? As we said, it takes a lot of land area, and it's fairly intermittent because you're only getting power when the sun is shining. Okay, I have to pick up the pace. So I did want to say just sort of quickly about wind. So wind is one of the more economic choices in terms of renewable energies. In 2018, there were 592 gigawatts of capacity installed globally. So solar was 505 gigawatts. So we've got slightly more wind than solar. But we've got a lot more wind than solar in Canada. So solar, we had 3 gigawatts. For wind, we have 13. And I just wanted to, this is just sort of a basic equation of how power is generated from a wind turbine. So really, it's a function of the density of air, which is not something we tend to think about maybe, but air does have a density, a weight per unit volume. So how much weight per unit volume does the air have? The area, the swept area, so that's when these turbines spin, it makes a circle, right? So you want the area of that circle covered by the blades times the wind speed cubed. So the wind speed to the power of 3, that's a very important variable, right? A small change in wind speed could have a big impact on your power generation. Okay, and then this figure here is showing, just like we have a solar resource distribution in Canada, we have a wind resource distribution. So not everywhere in Canada is equally well suited to generating electricity with wind. The darker purple is better, right? So wind power density, watts per meter squared. And so for a big sort of swath of the country, we've got light purple, right? And our best resources tend to be off the coasts, right? So here on the East Coast, some on the West Coast, a bit in the Rockies, right? We do, as I said, we do have a fair bit of wind installed in southwestern Ontario, and so it's a little bit hard to match up the colors. We're maybe around this range here, okay? Okay. So in Canada, our electricity generating system is already relatively low environmental impact. So as we saw those figures early on, right, where already a fair bit of our electricity nationally comes from renewable energy, largely due to hydro. But in terms of greenhouse gas emissions, in Canada, a lot of our greenhouse gas emissions come from space heating and from transportation. So for space heating, solar energy can also be used to provide heat. So on the right here, we've got a very simple diagram. It's showing passive solar heating. So this is very simple. It's just house design, right? So you can design your house so that in the winter, the sun comes into your house and helps heat it up. If you've got sun heating up your house, you don't have to run your natural gas fire furnace, right? You don't have to turn on the baseboard heaters. And then in the summer, you can put an awning over your windows and keep the sun out. So then you don't have to run the air conditioner as much because you don't have as much sunlight coming in. So just simple things like that. If you wanted to go a little bit, if you were building a new house and you wanted to design it specifically to take advantage of passive solar heating, you might have something like a thermal mass. So you might have concrete floors. The sun comes in the window all day during the winter, heats up the floor. The concrete absorbs the heat and is going to hold on to it. And then overnight, the floor will release the heat to the interior of the house. And again, you've cut down on the amount of natural gas you need to burn in your furnace. We can also use what's called an active solar thermal system. And domestic hot water systems are relatively common, maybe not common, are used more than you might think. We'll put it that way. So this is a picture of the solar collectors, one type of solar collector. There's different types. It looks a bit like a PV panel, but it works very differently. So this would go up on the roof. This sort of matches up with this diagonal gray line down here. What happens is a fluid is distributed through pipes behind the glass. So behind the glass layer, there's pipes zigzagging with a fluid. So the sun is going to hit these panels. There's an absorbing plate back behind the glass. The heat's going to be transferred to the fluid in the pipes, and then it's going to come down into your basement, and it's going to heat your hot water tank. Okay, and then once all the heat's been transferred to your hot water tank, the cooler water is going to come back and cycle back through this panel. Okay, so this might be used for preheating water, for example. So you may not want to get rid of your natural gas or electric water heater altogether, but if you had a solar thermal system installed, that would reduce the amount of electricity or natural gas that you need to provide your heating. Okay, one other method of heating is geothermal. So in this case, heat is transferred between the indoor environment and the ground, which might sound a bit weird because the ground is not room temperature, right? But using a working fluid, you can, in the winter, take heat out of the ground, transfer it to your space. Okay, so your space is heated using energy from the ground. You might need electricity to run a pump and a compressor. Okay. And then in the summer, it can do the opposite, and it can take heat out of your house and return it to the ground. So it's like works like a refrigerator does. At Ontario Tech, we have a fairly large geothermal system providing heat for the campus. So it's um, called a, or it's sized as a 1,500-ton borehole thermal energy storage system. So the borehole part, that's the vertical pipes going down into the ground. If it were a residential type system, you could have, again, vertical pipes, or you might have it horizontal, so it takes up a large area sort of just under the grass. Okay. But this one is showing the borehole vertical loop design. At Ontario Tech, we have 370 boreholes going down 180 meters, and altogether there's 150 kilometers of piping transferring fluid back and forth. So in the summer, when heat is being removed from the buildings, okay, so rather than just air conditioning, we can use the geothermal system to take heat out of the building. It's going to be stored in the ground, and then in the winter, we're going to take that heat back and put it back into the buildings to warm them up. Okay. The last area I wanted to talk about was transportation. So a lot of our again, a lot of our greenhouse gas emissions in Canada do come from our use of transportation, so burning gasoline and diesel just to get from point A to point B. One option to mitigate those emissions would be to electrify our transportation system, right? So use electricity because as we've seen, our electricity system is already pretty environmentally friendly. Another option is to use biofuels. So this can include ethanol and renewable diesels. So in Canada, we already do use biofuels. So we're sort of mandated to have at least 5% by volume renewable content in gasoline and at least 2% renewable content in diesel. So when you go to the gas station and put gas in your car, you're already getting some ethanol with that. There are designs of vehicles that can use much larger fractions of ethanol. So rather than 5%, you might be 80 or 85% ethanol. Ethanol is produced from crops. So in Canada, mostly from corn and wheat. Biodiesel comes from fattier types of plants. So soy or canola, waste cooking oil can all go to producing biodiesel. Because the ethanol and the biodiesel are organic, so the molecules are made up of carbons and hydrogens and other things. When you combust them, you do still get greenhouse gas emissions. The advantage to biofuels is that they, on a life cycle basis, so the life cycle going from, if we're talking about transportation, we often say from well to wheels. So if it were oil, it would be from where we took the oil out of the ground to where we combust it in our car. For plants, it's from the point where we plant the seed to where we combust the fuel in the vehicle. So with our biofuels, the GHG emissions from combustion, this carbon dioxide that we release when we burn ethanol, should balance the carbon dioxide that the plant absorbed while it was growing, right? We know plants need carbon dioxide to grow, so they're going to suck some carbon dioxide out of the atmosphere as they grow, and then we're going to release it again when we burn the ethanol. So if we look at the net greenhouse gas emissions, theoretically, you're net zero. Okay, there's a bunch of other emission sources involved, right? Because we need to process the fuel. We need to transport it from A to B. We need fertilizers to get the crops to grow. So it's not quite as simple as that, but that's sort of the idea behind using biofuels. Plus, we're not using a non-renewable resource, right? We can always plant more corn. And the last thing I wanted to talk about just very briefly was hydrogen. Hydrogen is an energy carrier, not an energy source. So it's technically not a renewable technology, but it can be produced from renewable technology. Currently, most hydrogen is produced from methane, from natural gas. So it's not a low carbon fuel. But if you did produce it from a renewable energy source, then it becomes a useful energy carrier, a way of storing energy and then using it. So this is one view of the hydrogen economy from a fuel cells textbook. Well, I've redrawn it, but that's sort of where the concept came from. So in this case, we're sort of ultimately using energy from the sun, collected either through photovoltaics or through wind turbines. So the sun is making the wind blow. We take the electricity from the renewable technologies. We use the electricity to generate hydrogen and oxygen from water. So an electrolysis process. We store the hydrogen. Then when we want it, we can run it through a fuel cell to generate electricity. And then the fuel cell is going to output water as a waste product. We can feed that water back into our electrolysis system, add more electricity, generate more hydrogen. So we get a bit of a loop here. So that's one way that hydrogen is useful in a renewable technology-based system. So I said previously, like solar only available when the sun shines, right? So you need maybe batteries to back it up. Another option would be to have hydrogen to back it up. So when the sun is shining, we run electrolysis, we produce hydrogen, and then we've got that energy stored for when we need it. Okay, so I will stop there. And I think I will come back to the main meeting here. Oops. Okay. So are there any questions? Oh, maybe I should.
It was a great presentation. Thank you.
Okay.
Very informative. I like the passion and the energy. I learned a lot. I think everyone else will.
Good.
Jennifer, Filipojenko here. I have a question for you. So based on what's happening now in Canada, well, the rest of the world, but in Canada in particular, with the price of the oil and shale gas so low, almost close to zero, do you think somehow this condition, which might, it's of course temporary, but there are discussions about making it a little bit more permanent, essentially to kill the oil industry. Do you think it might be somehow, there might be more hope to use, let's say, the natural gas, which has been produced so far for, let's say, power generation, instead to hook up better, with hydrogen production? Do you see a possibility there in terms of economical development?
I think there is an opportunity to shift away. Oil is tricky, right? Because it's driven by global markets. And so if the price of oil does remain low, it just doesn't become economic to produce as much, right? People will, if you can't make money producing oil and you can't keep people working, then we will need to shift to something different. And hydrogen is one option that I have heard people discussing. Hydrogen has a long history of being like almost the next, it's always the next thing, right? But if there was sort of a global shift away from oil, I'm not sure Canada alone would be able to do it, but if there was more of a global shift, then hydrogen, I think, could come in and play a bigger role than it currently does.
Okay, thank you.
Hi, Jennifer. This is Sharman. What is the current highest efficiency of solar panels?
I haven't looked recently at so NREL, the National Renewable Energy Lab in the US, they have a graph that they update periodically that shows sort of the highest research potentials that people have reached. Commercially, I think they're still around sort of 20% and below is where I think they still sit.
So how do you compare that with nuclear power plants, the efficiency?
So nuclear, probably know better than I do. I think nuclear may be around 30%. A conventional like fossil fuel fired plant would be sort of around the 30% range. A natural gas combined cycle where you're generating power both through a gas turbine and a steam turbine, that can be more 50%, 60% maybe. So they are compared to some of our conventional technologies, solar is quite low. Different cells have different efficiencies, right? So the monocrystalline silicon, that's quite low. I think that's the one around sort of 20%. Newer sort of multi-junction cells where you stack different cells of different materials on top of each other. So you've got more band gaps at play and you're able to use more of the solar energy based on the different materials. They can have higher efficiencies because they're able to use more of the energy from the sun. So solar's got sort of depending on the material that you use for the solar, it's got sort of a hard cap just based on the physics of how much energy the solar radiation has and how much energy the electrons need to move.
Okay, I see there's a question from Billy on chat line.
Okay. Is the general drive for 100% renewable energy a sensible policy? So my personal opinion, I'm rather skeptical of whether we could get all of our energy from renewable sources, especially in the near term. I know there have been research studies done where people have said that it is doable. I think there are a lot of challenges. I mean, even just politically, trying to find space to put, like, as I said, you need a lot of land area for some of these energy technologies, right? Even just trying to find a place to put them would be quite a challenge. So I would say not in the near term, at least.
So I have a follow-up question, Jennifer. Mm-hmm. So if you were to put a first colony on Mars, that's the challenge for this X hackathon.
Yeah.
Would you rather basically use a small modular reactor or would you use solar panels?
Is that my only energy source? Can I only have one or the other?
For sure.
So, I mean, I think if I were in a colony on Mars, having reliable energy would probably be one of my priorities, right? I think you probably want, for pretty much any system, diversification is key, right? You don't want to be entirely reliant on any one energy technology. And I think that would apply even on Mars. So if you had maybe a small modular reactor for most of your power needs, right? But then you're going to want something if the reactor needs to go down for service or if it breaks somehow, you don't want to be totally in the dark, right? So you want something backup. Nuclear, large-scale nuclear doesn't load follow well, right? So it's good for baseline power, producing a consistent supply over a long period of time, but power demand fluctuates, right? And so in Ontario, we make up that difference with hydro and natural gas and wind. On Mars, maybe you could modulate or control your demands enough that wouldn't be such an issue. But I think you probably want something to provide a little bit more flexibility, right? So something to run on top. And solar is, I have to think it's lighter than a small modular reactor, so it wouldn't be hard to get up to Mars. Oh, one thing I forgot to mention was like the new solar technologies, like thin film technologies. That would be very easy to transport, a little bit more robust. You wouldn't have to worry about like the glass breaking and that sort of thing. So I think maybe a new solar as an add-on to the SMR.
Okay, thank you. There's a question from Doreen on the chat line.
The solar load follow well. So solar doesn't, I would say solar doesn't really load follow at all. So if you wanted it to load follow, you'd have to have something like a battery or hydrogen on the side to store energy and release it as you want it. Otherwise, it's just sort of generating as the sun is out. Sometimes you see, more recently, there's been those big concentrating solar plants mixed with a natural gas plant, and the combination of the two of them would have more flexibility along that line.
Do you have any more questions? Anyone else? Okay, thanks a lot, Jennifer.
Thank you.
It was a very resourceful presentation. So I would recommend everyone to join our next presentation that will be conducted by one of our faculty members from our faculty, so on small modular reactor. In the meantime, I want to mention about our X Hackathon Challenge. I would appreciate if you can actually spread the word amongst high school teachers and students, and please ask them to come and register.